So if you recall, we said there were these four main categories of synchronizers. There were these atomic operations. There were mutual exclusion operations, of which atomic stuff is kind of a subset. We talked about coordination, making sure things run in the right order at the right time, under the right conditions, and barrier operations, things that coordinate groups of threads to do stuff as a group. We're going to start with the most basic things, which are the atomic operations and variables. And we'll discuss the programming language features and features that are part of the Java class library that provide atomic operations and variables. So atomic actions, which are very, very important at the core of all the concurrency stuff in Java, ensure that any changes that occur to fields or state or data, whatever you want to call them, are always consistent and will be made visible to other threads. So as we talked about, atomic action is one that either happens all at once or doesn't happen at all. The most important thing is it can't stop in the middle and leave things in an inconsistent state. What a nightmare. Any side effects of an atomic action aren't visible to other threads until the action is done. So that's why it's sort of all or nothing. So until it's finished, it doesn't actually show up or manifest itself at all. And that's very important, as we'll see. There are three key concepts associated with atomic actions in Java, and these are always great quiz questions, by the way. Oh, that reminds me. We'll probably have a quiz in maybe either next week or the following week. So just to give you a heads up, I don't like to go too long between the quizzes, otherwise you have too much stuff to study. But I also don't want to have quizzes every week because it becomes overwhelming. And we spend all our time quizzing and not enough time learning. So we'll probably do it in a week, and I'll let you know way ahead of time. The best way to study for the quizzes is to go back and watch the videos and look at the slides. One concept is atomicity, which basically says you have these indivisible effects, one nation indivisible, one value indivisible, with consistent behavior for all. This is an example, we already looked at this before, of not having things be indivisible. So if you increment counter plus plus and counter minus minus, those a plus plus and a minus minus may look indivisible visually when you look at the source code, but under the hood, there's actually multiple operations involved at the hardware or the Java virtual machine level. You read the value from memory, you increment the value, and then you write it back to memory. So it's actually multiple operations. The second concept is visibility, which determines when one thread can see the effects of another. So here's an example where we're going to have a Boolean, just a good old garden variety Boolean. It says done. And as the name of the class suggests, this loop may never end. Here we're going to have one method called work, which will run in one thread. So this is going to sit here in one thread and check to see if we're done. And over here, we're going to have another method called stop work. And this will run in a different thread. So remember we talked before about threads being like people and they can do work. Well, here's a good example where this thread is doing some work, and at some point it's going to call stop work. And this thread's going to do some stuff, and while it doesn't think it's finished, it'll do work. And the thing that's really curious about this is even if thread 1 sets done to true, thread T2 may never see that. And that's because in the absence of synchronization, there's no guarantee that the value that T1 sees of done will be propagated in such a way that the value that thread T2 sees of done will be updated to reflect the change. And that seems really crazy, doesn't it? It's like, but I set the code. It should be working. Well, sadly, that's not the way things work in modern multi-core processors that have lots of caching. And caching is there, of course, to make your life better because it should make things run faster. But if you have to coordinate, then you have to make sure you use your synchronizers to propagate the visibility of changes between the different threads running in different caches. And then ordering is what determines when actions in one thread occur in terms of their ordering relationships with respect to another thread. And this is even more crazy. So here we've got a class called badly ordered. Once again, it kind of gives away the problem here. We have two fields, two Booleans, A and B. Both are set to false. Here we have method 1, where we're going to set A and B to true, one after another. And then the question is, what will the values of R1, R2, and R3 be with respect to A and B if we read them in thread T2? Well, you would think that A will become true before B will become true, because that's what it looks like if you look at the ordering that we set them. However, there is no reason why the hardware, believe it or not, has any obligation whatsoever in the absence of synchronization to ensure that these things first ever propagate and become visible. But even if they do, the order in which they will become visible is not defined. So you might end up with all kinds of crazy results. You might see, this might be true, but B might be true, but A might be false, even though A was set before B. And that's because there's no restrictions on the ordering in which things are moved between threads if you don't use synchronizers properly. Isn't that totally insane? So you can imagine why inheriting a pile of code written by someone who didn't understand these subtleties of memory ordering and synchronization, and then having crazy results, you just go insane trying to figure out what's going on. And that's because of these concurrency issues. And that's by design. The designers of Java intentionally did it this way in order to take advantage of all the hardware optimizations. But they saved you because we have synchronizers to enforce the proper ordering. Okay, so that's kind of the issues. So the 3 issues are atomicity, visibility, and ordering. Those are the 3 primary concerns with respect to atomic actions in Java. So let's talk a bit about atomic actions. There's several types of them. One type is called a volatile. And volatile is actually baked into Java. That's part of Java, the Java language TM, right? If you get Java, you get volatiles baked in. And what they do, if you define a variable as being volatile in Java, which, by the way, is not at all related to the concept of a volatile in C or C++, go figure, but it's not. In C and C++, it has a different meaning. In Java, it means atomicity of reads and writes. So every time you read or write to a volatile variable, the value goes to or comes from main memory rather than from a cache. So it's basically like a write-through cache. You write through the cache to main memory. When you read from main memory rather than reading from the cache. So it basically is a flag saying, don't cache. Here's an example, sharing a field between 2 threads. So you can read more about this example here. This is a very simple program that alternates printing ping and pong between 2 threads. You notice we have 2 threads. This thread, let's call it T1, and this thread, let's call it T2. We start them, so they're both going to run, and it's got some code that's going on there. If you omit the the volatile type qualifier, that's the fancy name for that, then this program may never stop. But if you put volatile, then what will happen here is this thing will read through the program. You notice that they both have these loops that go from basically 0 to max. They're both doing that. And what we're doing is we're checking to see if this value equals that value. And if it is, we print pong, and then we update this with the current value of val. And then over here, we go through and we increment val. So this operation here, this setting of val equal plus plus LV is basically an atomic operation that will write through to main memory. So we're never caching this stuff. And so, believe it or not, this program will actually alternate printing ping and pong. Probably not the cleanest way of doing that. It requires knowledge of lots of low-level things. And it's very brittle because if you forget and take this volatile off, the program stops working. So volatile can be very useful in the hands of a person who knows what they're doing, but it's also fraught with peril. Other things you can do to get atomic behaviors are to use low-level atomic operations that are defined in the Java Unsafe class. And you can read about this class here. This class is a very infamous class. And in fact, the intent is to make it go away in the not-too-distant future in future versions of Java. This class exists to encapsulate low-level, very low-level hardware instruction mechanisms that atomically increment and decrement regions of memory. And it's really only designed for use by programmers of the Java class library itself, not by mere mortals like us who program applications and program normal programs. So we'll talk a bit about this stuff. It's really cool, but you normally couldn't use it. Underneath the hood, something called compare and swap is what's used extensively throughout the Java Unsafe class. I don't think I'm going to go through this in detail right here. I think I'll talk briefly about it at this point. But basically, this is an example of compare and swap. What it does is it takes a Java object, using the word loosely, an offset into the memory of that object, an expected value to find at that offset, and an updated value you'd like to set it to. And essentially, the way it works, and you can read more about it here at the compare and swap link, is that it runs this code atomically. So I'm writing it kind of in C-like format because that's kind of the way it's implemented under the hood. Obviously, this is not pure Java. And what this does is it runs this code atomically. And what that code does is it goes and sees what the value at that offset is. And if the value at the offset is what you expect it to be, then you update it atomically to the new value. And then you return the old value. Now, you might ask the question, what the heck does this do? And the answer is you can use these so-called compare and swap, or CAS operations, to implement lock-free algorithms, or non-blocking algorithms. And what that means is that the thread that runs them will spin and never block, which turns out in some situations to be exactly what you want. And we'll talk later about why you would do that. So here's a couple operations, lock and unlock. Lock takes an object and an offset and simply keeps going until the value is 0 at that offset, in which case we atomically set it to 1. So that's how you do lock in a lock-free algorithm, or a spin lock. We unlock something by simply setting the value at that offset to 0. So 0 means free, 1 means in use, and that's a super simple example of a spin lock. The synchronizers in the Java class library use CAS mechanisms extensively. And if you want to learn all the low-level details of why this is the case, it's actually really fascinating. Go take a look at this video by my good friend Doug Lee, who wrote the majority of the synchronizers and threading mechanisms that are available in Java. And he gives a really cool description of why they do all this crazy stuff. And the reason, in a nutshell, is because in modern multi-core processors, keeping the core busy is important for performance, because pausing cores and suspending them and then restarting them is very expensive in terms of computation time. A couple other things are atomic classes, which basically use the Java Unsafe CAS, compare and swap mechanisms we just talked about, to implement more powerful lock-free algorithms. So here's a simple example that you'll be using for the next assignment. Atomic Boolean. It has basically a way of keeping track of the offset into the object. This is some really crazy Java reflection code. I won't spend a lot of time on it, but it basically is figuring out the offset from the start of the object where the field value resides, which, as you can see, is defined as volatile. So we're using the Java reflection API. We make a volatile value. And then Atomic Boolean has a compare and set method, which is very similar to compare and swap, just a slightly different name. And you give it the Boolean that you expect and the Boolean you want to update to. And then under the hood, it goes ahead and calls compare and swap int in order to try to atomically set that Boolean variable to the value that you want it to be. And it returns true if it succeeds, whereas if it doesn't succeed, if it doesn't make that set stick, because it's currently in use, it returns false. You will end up using this mechanism in your assignment 1B because you're going to implement a simple spin lock to protect the Palantiri manager's internal state when multiple threads want to gaze on more Palantiri than we have. And then setting something, you can simply set it to some new value and it atomically updates it, and that's because value is volatile. So setting value to 0 will automatically free it, make it available. Setting it atomically to 1 will automatically make it in use, and so on and so forth. Okay, so miraculously, that is the end of that discussion.